Hi, welcome to AP Calculus for East Aurora High School. Today we're going to look at Chapter 1, Section 4, Discontinuities. Again, you've reviewed these from pre-calculus, so this should just be a review for you. Discontinuities fall into two different categories. We're going to call our discontinuities either removable or non-removable. The definition of a removable discontinuity is a discontinuity at C is called removable when the function can be made continuous by defining f of c. So what we see there is that there is just one point where the function is not continuous. If there is one point where the function is not continuous, what we are going to see on our graph is a hole in the graph. And we'll see with some of our examples how we know when there's going to be a hole in the graph and where the hole is going to exist. The second kind of discontinuity is called a non-removable discontinuity. A non-removable discontinuity is therefore going to be the opposite, a discontinuity that cannot be made continuous by just defining one point. So we're going to see that our non-removable discontinuities fall into two different categories. The first category is going to be a vertical asymptote on the graph. The second category is going to be what we call a jump discontinuity or a break in the graph, and we'll see some of the reasons that we end up with jump discontinuities as well in a few of the examples that we have today. Beginning with example number 1, f of x equals x squared minus 2x minus 3 over x plus 1. You'll notice that we have a rational function, and this rational function is going to have a place where the denominator is equal to 0. So this is going to be undefined when x is equal to negative 1. So what we are going to say then is let's examine x equals negative 1 and see what's going on at x equals negative 1. So we know that there has to be some kind of discontinuity there. We would like to figure out what kind of discontinuity is it going to be. So looking at the function, f of x is equal to, my numerator I can tell is factorable. So when I factor this numerator, it's going to be x minus 3 times x plus 1 over that denominator, x plus 1. This allows us to rewrite this function as an equivalent function that matches everywhere except for at x equals negative 1. So you'll notice that I can cancel off that factor of x plus 1. The factor of x plus 1 actually made the numerator and denominator both be 0. So if I were to go back to my original function and substitute negative 1 into the original function, I would see that I would end up in the numerator with 0 and the denominator with 0. As soon as I see that I have an indeterminate form and that these factors can be canceled, this tells me that I have a removable discontinuity. I am removing the discontinuity by rewriting this function as f of x equals x minus 3 and canceling off the x plus 1s. So now what I have here is actually the function f of x equals x minus 3. X minus 3 I know is a linear function, so the only place where I can't graph this function is at negative 1. I am going to use the newly written function to find where the hole is going to be. So I'm going to say x and f of x. If I start, for example, at negative 3, negative 2, negative 1 is going to be my problem spot, 0, 1, and 2. Substituting negative 3, and again, now it doesn't matter which function I substitute into, I should get exactly the same answer. The only place that it's going to matter is at x equals negative 1. So when I substitute negative 3 into this new function, I get negative 6. Negative 2 minus 3 is negative 5. But when I plug negative 1 in, I get negative 4. What that tells me is that my original function did not have a point here, but my new one does. So if I'm graphing my original, I am going to put a hole at negative 1, negative 4. Continuing on with my list, 0 minus 3 is negative 3, 1 minus 3 is negative 2, 2 minus 3 is negative 1. So graphing my original function f of x, I am going to have the following graph. Again, at negative 1, negative 4, I'm going to put a hole, and I'm even going to emphasize it by making it a red hole. And then the rest of the points follow along in a linear function. So this is the graph of f of x, and I'm going to identify that this hole is occurring at the point negative 1, negative 4, and that this is a removable discontinuity. Again, it's a removable discontinuity because I can simply identify a point at negative 1, negative 4. I can fill in that hole, and that would make this function continuous. So a discontinuity is called removable when all I need to do is to find one point to make the whole function continuous. Moving on to example number 2, I have the function g of x is equal to x plus 3 over x minus 2. Again, I start by looking at where this function is undefined. So this is going to be undefined when x is equal to 2. Now you'll notice when I go back to my original function and I try to find g of 2, g of 2 is going to be equal to 5 over 0. So if I only have a value that's undefined, not indeterminate, that tells me that I actually have a vertical asymptote at this spot. I don't have just a hole because the function is only undefined at 2. So on my graph, I'm going to draw in my vertical asymptote at x equals 2. Now a vertical asymptote is going to be a non-removable discontinuity. Because I can't simply make this a continuous function by identifying just one point. This discontinuity is at the vertical asymptote. Now I'm going to take a minute to make a table of values here and go ahead and graph this function. And again, you'll see that at 2, I'm not going to have a function value. My function is not defined at 2. So I'm not going to have anything at 2. Let's start, for example, at negative 1, 0, and 1, and then go beyond the vertical asymptote 3, 4, 5. Take a few minutes, fill in that table of values, plot the points, and come back and check your graph with mine and see if we match. Check your table of values and the points that you've plotted. And you can see that at x equals 2, my graph breaks apart at that vertical asymptote. So this is called a non-removable discontinuity. I would, of course, identify where that is happening. So I'm going to say I have a non-removable discontinuity at x equals 2, and this is a vertical asymptote. In example number 3, we can see that there are some functions that are going to have more than one discontinuity. So in example number 3, we have h of x is equal to x minus 1 over x squared plus x minus 2. So I'm always going to start by making my denominator equal to 0 and find out where I'm going to have the function be undefined. So setting my denominator x squared plus x minus 2 equal to 0, I see that this quadratic is factorable, so I factor it into x plus 2 times x minus 1. Setting each factor equal to 0, I see that this graph is going to be undefined at x equals negative 2 and at x equals 1. Now let's see what kind of discontinuities we have by substituting those values into our original function. So when I substitute negative 2 in for x, I see that my numerator is giving me a -3, but my denominator is giving me a 0. So if just the denominator is 0, if this function is undefined at -2, that tells me I have a non-removable discontinuity. I'm going to abbreviate a little bit there, and this is going to turn out to be a vertical asymptote at x equals -2. For the second function value at h of 1, I see that I'm getting 0 over 0. 0 over 0 is my indeterminate form. So if it's an indeterminate value, that tells me that I have a removable discontinuity at x equals 1. So we are going to be able to remove that discontinuity. We're going to find where the hole is going to exist. So going back to my original function h of x, I've rewritten it as x minus 1 over x plus 2 times x minus 1. So I can see that the x minus 1 factors can be canceled off, and that tells me that my newly written function is going to be 1 over x plus 2. I'm going to use that function to find where the hole is going to exist. I know that it exists at x equals 1, so if I find h of 1 now, I'm going to get 1/3. So substituting 1 in here, the hole is going to exist at 1, 1/3. Let's find the rest of the function values. So I'm going to make a table of values here so that I can graph the rest of this graph. So let's start back at -4, -3, -2 is my vertical asymptote. -1, 0, 1, 1 is going to be the hole, and then 2 and 3. So take a few minutes and fill in your table of values, plot the points, remembering to put a hole at the point 1, 1/3. And again, the only way we're going to get the y-coordinate of that hole is by canceling off the x minus 1s and using our newly written function 1 over x plus 2. So I've filled out the table of values. Notice that I've plotted the points. I see a vertical asymptote at -2 where I have a non-removable discontinuity, and I see a hole at the point 1, 1/3 where I see a removable discontinuity. Two things are very important when we are identifying discontinuities. First of all, we have to make sure that we tell what kind of discontinuity we have at each spot. And secondly, we have to make sure that we're telling the x-coordinate for those discontinuities. Lastly, whenever we have a hole, we are going to have to make sure that we find the y-coordinate of the hole so that we can graph it correctly. Our last two examples are going to be examples of other non-removable discontinuities. These, however, are not vertical asymptotes. Instead, they are sometimes called jump discontinuities. And you'll see when we do the graph why that name makes sense. So for number 1, I've got a step function. Think back to pre-calculus and some of the times that you ended up with a step function. This may not be one that you've seen before, however. I've got f of x is equal to the absolute value of x divided by x. So we want to get a feel for what this graph looks like. I want to go ahead and make a table of values, noting that my function clearly is going to be undefined at x equals 0. I see even further that not only is it going to be undefined, it's going to be indeterminate because it's going to be 0 over 0. However, this does not make it a removable discontinuity. So instead, let's plug in some x values, substituting them into my function. I want to try -3, -2, -1, and then 1, 2, and 3. So when I use -3, the absolute value of -3 is 3, but 3 divided by -3 is -1. So the output is -1. Now try -2. The absolute value of -2 is 2, but 2 divided by -2 is also -1. At negative 1, the absolute value of negative 1 is 1. 1 divided by negative 1 is negative 1. So to the left of 0, all of my function values are negative 1. I'm going to go all the way over to 0 and say that at 0 there isn't a function value. So I'm going to put a hole in the graph there and say all the rest of my function values were negative 1 to the left. Now let's look to the right of 0. So at 1, the absolute value of 1 is 1. 1 divided by 1 is 1. Absolute value of 2 is 2. 2 divided by 2 is also 1. Absolute value of 3 is 3. 3 divided by 3 is also 1. Again, starting at 0, I'm going to have no function value, but everything to the right gives me a function value of 1. I'm not even going to just start this at x equals 1. I've got to start over at x equals 0 because I'm going to get a function value of 1 for all the fractions between 0 and 1. So you can see that this graph is discontinuous at x equals 0. What kind of discontinuity is it? It is a non-removable discontinuity. It is a non-removable discontinuity at x equals 0 because we can't just define one point that would put these two pieces together. These two pieces have a jump discontinuity between them. One branch jumps to the other. So therefore it is a non-removable discontinuity. Our last example is a piecewise function. And while some piecewise functions are continuous, others will be discontinuous. So it's going to be important for us to analyze each one individually. This one, g of x is equal to x plus 2 when x is less than or equal to 1, and g of x is equal to x squared when x is greater than 1. What I'm going to do is graph both of these branches and see if the branches come together. We clearly can see that at x equals 1 is going to be the only possible place where I could have a discontinuity. What I like to do when I'm graphing piecewise functions like this is put that number 1 on both sides of the graph, deciding which point will be a solid dot and which point will be an open circle. So let's start with x plus 2, where x is less than or equal to 1. So I'm going to have x values of negative 2, negative 1, 0, and 1. Substituting into the function x plus 2, because that's the part of the function that's defined for x is less than or equal to 1, negative 2 plus 2 is 0, negative 1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3, and because I see that I have a less than or equal to, there is an equal to there, that tells me that that point is going to be a filled in circle. So I'm going to go ahead and graph those. Negative 2, 0, negative 1, 1, 0, 2, and 1, 3 is going to have a filled in dot. The rest of the graph is going to go down like this. It's a linear function. Now let's go beyond the number 1. I'm still going to use the number 1, even though 1 is not part of the domain, for the x squared function, because I want to know what happens at the beginning of that interval. Let's go 1, 2, 3, and 4 for my input values. I'm substituting into the function x squared. So 1 squared gives me 1, 2 squared gives me 4, 3 squared is 9, and 4 squared, of course, is 16. Now, I, of course, see that at 1, 1, this time I'm going to have an open circle because x is greater than 1 is the domain. So 1, 1 is going to be an open circle on my graph. 2, 4 is going to be on my graph, and I see that this is a quadratic function, so I know that it's a parabola looking something like this. Now, clearly I can see that at 1, these two branches do not come together. Since the two branches do not come together, I'm going to say there is a non-removable discontinuity. At x equals 1. So this particular piecewise function did not come together at x equals 1. This again would be called a jump discontinuity. the two pieces jump. So hopefully this has been a good review for you of removable and non-removable discontinuities. We'll be working on these in class for the next few days, so it's very important that you understand the terminology that we are using and how we determine whether we have a removable or a non-removable discontinuity on a graph, because this is going to be important for us throughout the whole year in AP Calculus. Thanks for working with me today, and we'll see you next time. Bye-bye.